Good afternoon. My name is James, and today I will present our final project for EEE5053 computer vision. Our project is titled 4K Video Frame Generation via Motion Adaptive DIS MCFI and CNN Refinement. The task is to generate missing 4K odd frames from a VVC-compressed scalable bitstream. We are given two inputs, 4K even frames from the enhancement layer and Full HD odd frames from the base layer. Our goal is to synthesize the missing 4K odd frames between each pair of even frames. The evaluation metric is BD rate against the VVC for upscale baseline. A negative BD rate means we outperform the baseline. The method also has a strict complexity budget, no more than 200,000 multiply accumulate operations per output pixel. The main challenge is that this is not clean natural video. It is 10-bit VVC compressed content, and the encoder introduces coding tree unit block artifacts on a 128-pixel grid. These artifacts dominate feature matching in optical flow and neural video frame interpolation methods. We tested more than 30 state-of-the-art VFI methods on Zombie Climbing 2, and all of them produced positive BD rate, often 40 to 80% worse than the baseline. This showed that off-the-shelf VFI does not work in this domain. Our final result is -33.96% average BD rate on the 4 known sequences, while satisfying the Mac budget. Including 2 hidden sequences, the 6-sequence average is -35.33%. The lightweight CNN refinement contributes 7.5 percentage points on average compared with the non-CNN baseline. The core idea of our method is motion adaptive routing. Instead of applying one universal method to all videos, we first classify the motion type of each target frame. For each odd frame, we compute the mean absolute difference between the two surrounding even frames after downsampling. If this value is below 30, the motion is low, and we use the DIS path. If it is 30 or higher, we compute the ECC affine correlation, called ρ. If ρ is at least 0.95, the motion is mainly global camera motion, so we also use the DIS path. If ρ is below 0.95, the frame has large non-rigid motion, and we use the block matching STVSR path. The DIS path uses dense inverse search optical flow from OpenCV. The key improvement is a symmetric formulation. We compute forward flow from the previous even frame to the next even frame, and backward flow in the opposite direction. Then we combine them to estimate midpoint motion. This is more stable near motion boundaries than a single unidirectional flow. Another important detail is that we run DIS at Full HD, not at 4K. When 4K frames are area downsampled to Full HD, each 2x2 block is averaged, which suppresses CTU artifact energy by about 6 decibels. This makes optical flow more reliable on compressed content. With the full pyramid in variational refinement, Symmetric DIS gives the best result among our classical flow configurations. For low motion and camera motion sequences, we further refined the DIS output using Refined CNN 14L. This is a lightweight residual CNN with 14 convolutional layers, 64 channels, and 3x3 kernels. The input consists of the DIS interpolated luminance frame and the 2 neighboring even frame luminance images. The network predicts a tan residual, which is upsampled and added to the DIS output. This residual design is important. A direct output CNN that predicts the full luma value collapsed toward temporal averaging. The residual formulation keeps the output anchored to the already reasonable DIS interpolation and only learns the correction. Refined CNN has 445,000 parameters and costs about 111,000 max per 4K output pixel because it runs at Full HD. The CNN improves precision from -25.4 to -31.3% and AMS05 from -45.6 to -51.8%. The zombie sequence requires a different path. Optical flow fails there for 3 reasons. First, the 128-pixel CTU grid creates strong periodic matching peaks. Second, about 80% of the frame is static background, so the moving zombie foreground is treated as an outlier. Third, deblocking hurts because compression artifacts are also useful texture for matching. For this case, we use block matching aligned spacetime video super resolution. We perform full search block matching at full HD using block size 16 and search range 32. Block matching is used only for alignment, not direct interpolation. We compute a confidence wave from the normalized SSD to mask unreliable blocks. Then we inject high-frequency information from the aligned even frames into the VVC for upscaled base frame. We also use AMTG, a neural VFI model, but only after domain adaptation. Since AMTG was trained on clean 8-bit video, we fine-tune it on the zombie sequence for 80 epochs. To satisfy the complexity budget, we run AMTG at 960 by 540 and upsample the result to 4K. Then a 6-layer residual CNN fuses the BMS-TVSR output and AMTG output. This gives a large improvement on zombie. BM alignment with confidence weighting reaches -3.71%. Fine-tuned AMTG reaches -8.61%. The final residual CNN improves zombie to -17.25%. A key finding is that one universal CNN does not work across motion regimes. In Leave One Out testing, applying a DIS-trained universal CNN to zombie-type content caused a regression of 13.3 percentage points. This confirms that the DIS path and BM path must remain specialized. The final 4 sequence results are zombie climbing 2, -17.248% per session, -31.291%, walk-in park, -35.463%, and AMS05, -51.837%. The average is -33.960%. For the hidden sequences, football large advert achieves -28.37%, and H3_AMS08 achieves -47.77%. The 6-sequence average is -35.33%, which is within 1 percentage point of the TA optimal result. Both paths satisfy the computational constraint. The DIS path costs about 116,000 max per pixel. The BM path costs about 175,000 max per pixel. The critical engineering decision was running AMTG at 960 by 540. At full HD, it would exceed the budget by a large margin. To conclude, our method achieves strong BD rate reduction while staying within the 200,000 max per pixel limit. The main lessons are, optical flow must be adapted to compressed content, residual CNN refinement is more stable than direct prediction, and per-sequence routing is better than a single universal method. For future work, the main remaining challenge is zombie climbing 2. Closing the gap would likely require training optical flow or VFI models directly on VVC-compressed data from scratch. Thank you. I am happy to take questions.